Hello and welcome again to CHeM in 3. In today's episode, we follow up on how to write rate laws or rate expression, extending from our last lesson where we looked at equations like this for multi-step reactions. But in that last lesson, the fast reaction came first and the slow rate determining step was placed second. But in this example, we look at how the rate law or the rate expression would be derived when you have the slow or rate determining step as the first of two reactions. And in this case, the rate of the reaction is going to be directly related to these two in the rate determining step or the slow step, but the final product would be E. The summary equation for the reaction would look like this, but the rate law or the rate expression would be based on the concentration of these individual reactants, making this particular reaction first order with respect to A, first order with respect to B, and overall a second order reaction. But what about a reaction with three steps, where the first one is fast, the second one or the rate determining step is slow, and the third one is also fast? If you remember the principles from the last two examples going back to the previous lesson, then you would know that this equation here is a summary, and the rate law or the rate expression can only include reactants. So these final products are included up here in this equation, and the reactants that are included here in this summary equation come about because NO is reacting with another NO. So it's easy to identify the rate determining step, or the RDS. That, of course, step 2. But what is the rate law? A student hypothesized that the order of the reaction with respect to H2 is 2. Evaluate this hypothesis. Now, this hypothesis given by the student is based on looking simply at this summary equation and seeing that you have a 2 in front of the H2, and then assuming that the reaction is going to be second order with respect to H2. But if you follow the principles of how to write the rate expression for this multi-step reaction, you would realize that everything must be centered on this slow or rate determining step, looking at what molecular entities go into producing the products of this rate determining step. And here you can see that one NO is involved, and it's actually reacting with an X. That X comes from where? That X cannot be a part of the rate expression because intermediates are not included in the rate expression. So we need to look at where X came from. And X came from an interaction between one NO and one H2. So based on that, it follows that the rate expression would be rate equals K multiplied by the concentration of NO to the power of 2, because you have two NOs, one which gives rise to X and the other one involved in the slow or rate determining step. And then, of course, you have to include a single H2, which is involved in this fast step, which produces X, which is a part of the slow or rate determining step. X itself, being an intermediate, is not included in the rate expression. So the second part of the rate law would be just H2. So then the hypothesis as given by this student would be wrong, because the student is making the assumption that because there is a 2 here in the summary equation for the process, that the rate expression could be derived from the summary equation. But this rate expression can only be derived from experimental evidence, which can allow you to determine the rate determining step. And when you determine the RDS, then you must analyze all of the steps, always remembering that going into the rate law, you can only have entities that are shown as actual reactants in the summary equation. So x cannot be a part of the rate expression or the rate law. But because x is a part of this slow step, you must look at where x was derived from. And these two entities must form a part of the rate law, with one NO being included here, the H2 being included here, both of these giving rise to x, and then the other entity in the rate determining step that interacts with these two which produce x is the second NO. So with the two NOs, you get this part of the rate expression, and with the hydrogen, you get this part. So this then should be the rate expression or the rate law, and the student's hypothesis is faulty because it is based on trying to derive the rate expression by looking at the summary equation. And this is not the way that you determine the rate expression. To determine the rate expression, you must carry out an experiment, collect data, and verify the reaction mechanism.